right? So if you use two coherent sources which are in phase with each other, this is the kind of pattern that you get. Distance between the sources is small d, distance from sources to the screen is capital D, and capital D should be much greater than small d to be able to observe the pattern clearly. Okay. Now, here we considered coherent sources, means their frequencies are equal. And if frequencies are equal, since waves travel in the same medium from both of them, the wavelengths will be equal. That is why the path difference at the point O will be 0, and you will get a maximum constructive interference. Okay. And similarly, you know what is the path difference at other points and all. Now, what do you think will happen if we insert a glass slab in front of one of the sources? Suppose a glass slab like this is introduced. Its refractive index, let's assume, is mu, and the thickness of the slab is T. As a result, what happens to the uh, interference pattern that you see? Will the pattern stay the same? Will the pattern move upwards or downwards? Okay, Pradyun is saying it will shift because optical path increases. Fine, fine. Can you tell me, like, how the glass slab disturbs the waves, or how it alters the waves? Any one of you? What will the difference be between waves traveling in air or vacuum, and waves traveling through a glass slab? Okay, I got one answer as it makes the waves move slower. Okay, that makes sense. Light travels slower through glass than through air or vacuum. That is correct. So wave speed decreases. Fine. As a result, what happens to the wave? Okay. Pradyun, what you are saying is correct. Uh, See, we have sources of equal frequency, right? Irrespective of the medium in which the wave travels, the sources will continue emitting waves at the same frequency. Let's say they emit, fine, actually for light, the frequency will be very, very high. Okay, in megahertz and all it will be. Let's consider a normal example. Okay, normal a real life oscillating source, mechanical oscillating source. Let's say it oscillates 10 times in 1 second. Okay, so it produces 10 pulses in 1 second. Now, irrespective of the medium in which waves travel, the frequency will remain the same. But the speed with which waves travel changes if the medium changes. Okay. Here the sources S1, S2 emit waves of same frequency, but the waves going from S1 to the screen travel only through vacuum, okay, or air. But the waves emitted by S2, they first have to travel through a glass slab and then through air. Now, while traveling in a glass slab, the speed will be less, and we know V is equal to F lambda. If speed decreases, correspondingly or proportionately, wavelength will decrease. Therefore, the waves arriving at the screen from S1 and the waves arriving at the screen from S2 will not exactly be the same. As long as the wave travels inside the glass slab, its wavelength will be shorter. Okay. Let us look at this in detail. Suppose this is the reference line, okay, that perpendicular bisector between the two sources. Assume the screen is here, and let's say the source S2 is here. We are, okay. You can imagine S1 also at the same distance above that perpendicular bisector line. Now, normally this point O is the central maximum. Okay. Why? Because the distance from S1 to O is same as the distance from S2 to O, and not just because distance is same. If distance is same, the phase difference uh, or the phase with which the waves arrive from S1 and the phase with which the waves arrive from S2 will be the same. Okay, they'll interfere constructively. Okay, because they arrive there at the same phase. Now we had discussed all this, the relation between distance and phase change in a single wave. Okay. Suppose from S1 to O, the distance is some, let's take 5 wavelengths. Okay, so 5 pulses will fit between S1 and O. Something like this. Okay. Had the medium been the same, from S2 to O also exactly 5 pulses would have traveled. Okay, because the distances are same, wavelengths will be same. If you introduce a glass slab in front of one of the sources, let's consider a thick glass slab like this. Refractive index mu, thickness T. As long as the waves travel inside the glass slab, the wavelength will be lesser. So if wavelength decreases, what happens? Some extra pulses will fit in that space. Without the glass slab, between S2 and O, exactly 5 pulses would have been present. But with glass slab, suppose the wavelength becomes half or something, then here you will see more number of pulses. Exact number we cannot say, it depends on the thickness and refractive index. Okay, I am taking 2.5 pulses in this space. And after that, the length of the pulses will be the usual length. So there's no guarantee that they will still arrive there in phase. The glass slab introduces a phase difference, or it gives rise to a phase difference with which the waves arrive at the point O. Okay. So we need to find out with what phase difference they arrive there. What happens to the interference pattern? Let's see. Now, normally the number of pulses between S1 O would have been equal to number of pulses between S2 and O. Due to the introduction of this glass slab, how many extra pulses are introduced is what you need to find out. Because for each pulse, you will be introducing a phase difference of 2 pi. Okay, so the wave arriving at O from S1 and the wave arriving at O from S2 will have a phase difference depending on the number of extra pulses. Okay, now how to find out the number of extra pulses that get introduced? Now we know that these are all small angles. See, this diagram is an exaggerated diagram actually. The two sources are very close to each other and the screen is very far. Okay. So the wave traveling from S1 and the wave traveling from S2, they travel almost parallel to that, what is that, perpendicular bisector. Okay. So this thickness T, in that thickness, normally a certain number of pulses would have been present. Normally means when there is no glass slab introduced, in that distance, a certain number of pulses would have been present. If the glass slab is introduced, in that same distance, some new number of pulses will be present. Okay. So if you can find out what is the change in the number of pulses in that space, then you can tell what is the phase difference with which they arrive at the point O on the screen. That's the logic. Okay. Now, in air, okay, air or vacuum, let's say the wavelength is lambda. Then in glass, the wavelength will be lambda divided by mu. Okay, because mu is inversely proportional to wavelength. So mu1 by mu2 will be equal to lambda 2 by lambda 1. Based on this, you can tell refractive index of air is 1. And in glass, the wavelength will be lambda by mu if wavelength in air is lambda. Now we want to know how many pulses will usually be in that distance t. Okay. Now if wavelength is lambda and distance is t, the number of pulses that would have been present usually will be t divided by lambda. For example, if wavelength is 2 meters and the thickness is 10 meters, I'm not talking about light waves. Okay. Generally, wavelength is 2 meters, distance is 10 meters, then 5 pulses will be there. So distance divided by wavelength. Same thing here. So without glass slab, in that thickness T, the number of pulses you would have seen is T by lambda. Now with the glass slab, the number of pulses you will see in that thickness is T divided by the new wavelength. The new wavelength is lambda by mu. So the number of pulses you get will be mu T divided by lambda. And mu for any medium other than air is greater than 1. Therefore, N2 will be more than N1. That is what we see in this picture also, diagram also. Without glass slab, lesser number of pulses in that distance. With glass slab, more number of pulses in that distance. N2 greater than N1. Now, we don't need the exact number of pulses. We need the extra number of pulses going from S2 compared to the number of pulses from S1. So the extra number of pulses that arise due to the introduction of glass slab will be N2 minus N1. That is mu minus 1 into T by lambda. Mu T by lambda minus only T by lambda, that is mu minus 1 T by lambda. These many extra pulses are introduced. Now for each extra pulse, you will get a phase difference of 2 pi. Then if these many extra pulses are introduced, the phase difference with which the waves arrive at the point O. Okay. So the phase difference at the point O becomes the number of extra pulses multiplied with 2 pi. So that is mu minus 1 T by lambda into 2 pi. That's the phase difference you will see at the point O. Therefore, the central maximum will no longer be the central maximum. I mean, the point O will no longer be the central maximum. Okay, the waves arrive there with some non-zero phase difference now. The point where the waves interfere with zero phase difference is what we call the central maximum. Okay. Now you can see what happens. From the lower side, there is a greater number of pulses compared to number of pulses from the upper side. That is why O cannot be the central maximum anymore. So where will the central maximum go? Will it shift upward or downward? Any guesses? Will the central maximum shift to the side of S1 or to the side of S2? I got one answer as to the side of S2. Fine. So remember the idea. Okay, that is correct only. The number of pulses have to be the same. Okay. At whichever point on the screen, the number of pulses from S1 and the number of pulses from S2 are equal, that point is the central maximum. Okay, Pradyun, you changed your answer. I don't know why. Anyway, the earlier answer is only correct. Uh, if you take a point on the perpendicular, if you consider this point O, to the point O, the number of pulses from S2 will definitely be more than the number of pulses from S1. Distances are equal, but S2 has a glass slab in front of it. So extra pulses are introduced. You take any point on the upper side. Okay, let us extend the screen a little bit. You take any point on the upper side. Now, some number of pulses will reach there from S1. Some number of pulses will reach there from S2. Now, from S2, the distance is already greater if you take a point above O. And on top of that, there is a glass slab also in front of S2. Now, due to distance itself, the number of pulses from S2 is going to be greater. If you introduce a glass slab, some more pulses will get added. So there is no way the number of pulses from S1 and number of pulses from S2 can be equal at this point. Okay. So anywhere above O, it's not possible. It has to be below O itself. Now you take some point here. Waves will be arriving there from S1 as well as S2. From S1, the distance to that point on the screen is greater. Okay. From S2, the distance is shorter, but S2 has a glass slab in front of it, which will allow extra pulses to be present here. So this way, there is a chance that the total number of pulses from the two sources is equal. Okay. From one source, the distance is greater. From the other source, the number of pulses will anyway be greater because there is a glass slab. Okay. So this is where the central maximum will now be. So basically, if you put glass slab in front of the lower source, the pattern will shift downwards. Had you put the glass slab in front of S1, okay, the pattern would have shifted upwards to the side of S1. So you just have to think in terms of number of pulses. Based on that, you can tell what will happen to the pattern. Okay. We can even tell how much exactly the pattern will shift. By what distance it shifts also we can calculate. Okay, let's see how that can be done. Now, usually this is the pattern that we get. Okay, just a moment, let me copy this. If sources are in phase and coherent, this is the pattern that we get on the screen. Just a moment, Pradhan is asking, the number of wavelengths should be the same or the distance should be the same? Distance is definitely not the same, no? If you take this point on the screen, the distance from S1 to that point is definitely not same as distance from S2 to that point. It's the number of pulses that has to be equal. Yeah, phase difference should be 0. Actually, okay, I'll explain a little later. So this is the normal YDSE pattern that you expect to see on the screen. If there's no glass slab introduced, you will get a pattern like this. Now, due to the introduction of glass slab, okay, in front of the lower source, we have just found, okay, or we have just discussed that the pattern will shift downwards a little bit. So let it go down like this. So this is when there is no glass slab. This is in the presence of glass slab. The entire pattern will shift down a little bit. Okay. Now, how much I can't say a little bit. How much it shifts depends on the thickness of the glass slab and its refractive index. But you can find out how much it shifts. How to do that? Originally, the central maximum is here. Okay, observe this carefully. Originally, this is the position of central maximum. Let's call this as O1. The new central maximum is somewhere here. O2. It has shifted downwards a little bit. This shift is what we are trying to find out. Let's call it as delta Y. Okay. Now what happens by placing a glass slab, we are introducing a phase difference. Originally at O, okay, the original central maximum that is there, at O the phase difference would have been 0. And somewhere below, or like if you go to any point below O on the screen, there will be non-zero phase difference. Okay, I'm talking about the situation where there's no glass slab. For O, there is no phase difference, and below O or above O also there will be a phase difference introduced. Now, by putting a glass slab, you know you are introducing this much phase difference. mu minus 1 t by lambda into 2 pi. Let's say this turns out to be pi. After calculation, assume this comes out to be pi. So you have introduced a phase difference pi. At which point? At the point O, they will now be arriving with a phase difference pi. That's fine. Let it be. In the original pattern, okay, when there's no glass slab, in the original pattern, this position, okay, the first minimum on the lower side is where you have a phase difference of pi. Phase difference pi means destructive interference. That is why you get a minimum there. Okay. At O, the phase difference is 0. At this point, let's call this point as A. The phase difference is pi. Okay. At B, the phase difference will be 2 pi. That is where they undergo constructive interference again. And so on. That's the pattern. So originally, when there's no glass slab, let's say you would have obtained a phase difference pi at this point A. Okay, not let's say. You would have obtained. Okay. Now, when you introduce a glass slab, assume you are introducing a phase difference pi in the waves reaching O. So now what happens? The pattern shifts downward. The exact point to which the pattern shifts will be this point. Where you would have normally had a phase difference pi, you will now have a phase difference 0. So how to find out to which place the central maximum will shift? You have to find out where that much phase difference would have arisen in the normal pattern. Okay. Normal pattern, the point O is point of 0 phase difference. As you go down, phase difference increases. Let's say by putting the glass slab, you have introduced a phase difference of pi. Now in the normal pattern, wherever you get that much phase difference pi, central maximum will now go to that place. That's all. Is this idea clear to all of you? To find out how much the pattern will shift, you need to know what phase difference you are introducing by putting the glass slab. How do you find that out? You have to find out number of extra pulses. Glass slab thickness, let's say it is T. Then in the absence of glass slab, you would have had T by lambda pulses in that thickness. In the presence of glass slab, you'll have T by lambda by mu. That is mu T by lambda number of pulses in that distance. So the extra pulses you have introduced are these many. For each extra pulse you introduce, you will be introducing a phase difference of 2 pi. Okay. In the waves arriving at O. Normally waves arrive at O with 0 phase difference. But if you put a glass slab, then depending on the number of pulses, they arrive at O with this much phase difference. Fine. Mu minus 1 t by lambda into 2 pi. For each pulse, it is 2 pi. For these many pulses, it will be this into 2 pi. Now, in the normal pattern, okay, in the original pattern, at some point on the screen, you would have already gotten this phase difference. The central maximum will go to that place on the screen. That's all. Fine, let's solve one question based on this. Suppose refractive index of glass is 3 by 2. You find out the thickness of the glass slab, okay, that must be placed in front of S2 such that the pattern, okay, the entire interference pattern shifts by a distance of, how much shall we take? 3 lambda capital D by 2D, where lambda is the original wavelength of light in air or vacuum, capital D small d, you know. So we are placing a glass slab of refractive index 3/2 in front of one of the sources such that the pattern shifts by this much distance. Find out what the thickness of the glass slab should be. Try this. I'll give you all 2 minutes. Basically, what happens when you introduce a glass slab is you'll be introducing a phase difference with which the waves arrive at O. Now, the phase difference with which they arrive at O, you should find out that first. Let us do that. The phase difference at O will be mu minus 1 into T by lambda. This is the number of pulses that you have introduced, extra pulses, multiplied with 2 pi is the phase difference that you will introduce. Okay. So the waves will now interfere at O with this much phase difference. Somewhere else they will interfere with zero phase difference. That somewhere else is what we want to find out. Okay. Where that happens? Usually, okay, let's call this phase difference as delta. Okay, let's call this phase difference delta phi itself. Usually for O, the phase difference is 0. Somewhere else on the screen, you will get that phase difference delta phi. Now, at O, you will get delta phi, and that at that somewhere else point, you'll be getting zero phase difference. So this is the place to which the pattern or the central maximum will shift. This distance is what you are expected to find out. Now, how do you do that? You should know how to relate y coordinate and phase difference at a particular point. If you know how to do that, then you know where the central maximum has gone. And how are y coordinate and phase difference related? In YDSE, if you assume the screen is far away from the sources, we know y is delta x capital D by small d. This is y coordinate in terms of path difference. And how do you relate path difference to phase difference? Delta x is delta phi by 2 pi into lambda. That's the phase difference, capital D by small d. So generally in YDSE, this is how y coordinate is related to the phase difference. That's all. Now, what is the phase difference we are looking for? This much. At whichever point this much phase difference is observed, central maximum will go to that point. So substitute this here. That's all. So 2 pi will get cancelled. Therefore, the point to which the central maximum shifts will be, okay, let me write everything. Mu minus 1 T by lambda into 2 pi. That's the delta phi. What are we left with? Lambda capital D by 2 pi small d. Okay. Wavelength also cancels. So we are left with mu minus 1 small t capital D by small d. Okay. And we wanted in the question, the pattern, it was told to you that the pattern has to shift by 3 lambda d by 2d. That's all. Simplifying this, you will get the thickness. Capital D, small d cancel. Thickness will therefore be 3 lambda by 2 into mu minus 1. As expected, it is in terms of wavelength. So if you introduce a glass slab of this much thickness, you can get a shift in the pattern of this much. But remember the idea. Okay, it's not like remembering a formula or anything. What is the original pattern? Okay. In the original pattern, where do you get that phase difference? If you know that, you can tell where the central maximum will be in the new pattern. Simple. And how do you tell where that phase difference will be obtained in the original pattern? You need to know the relation between y coordinate and phase difference. So this is very important anyway. For normal YDSE questions also, okay, you'll be using this quite frequently. Relation between y coordinate and path difference, and relation between y coordinate and phase difference. Okay. In fact, if you want to tell intensity at any point on the screen, amplitude at any point on the screen, for all such calculations, you'll have to use this formula. At any point on the screen, any point means any y coordinate, you should know what is the phase difference with which the waves arrive. Then only you can tell what is the effective intensity there, effective amplitude there, and all those things. Okay, fine. Just a moment. So if you have two sources like this, which are coherent and in phase with each other, then you can expect to see a pattern. What if the sources are coherent? Okay, coherent means equal frequency. Equal frequency means they'll emit waves of the same wavelength. Okay. What if they're coherent but not in phase with each other? What will happen to the pattern? Will it still be the same or will there be any difference? Think carefully and answer. Okay. My question is, what if the sources are not in phase? How will the pattern change? Okay, listen. At the beginning of this chapter, we had discussed this. Suppose these are the sources now, S1 and S2. In this diagram, the sources are in phase. Okay, S2 has just produced a trough. S1 also has just produced a trough. They are in phase with each other and they will arrive at the point P also in phase because point P is on their perpendicular bisector. So it's actually like the point O in our usual YDSE diagrams. Okay. So if sources are in phase, they'll arrive at O in phase. If sources are not in phase, this is what you will see. Let's call that point O itself. Pradyun, I'll take your doubts a little later. Just a moment. So if sources are not in phase, now look at this diagram. Here, S2 has produced a trough. S1 has just produced a crest. Okay. So there's a difference in the phase of the sources. And if there's a difference in the phase of the sources, then at their at a point on their perpendicular bisector, they won't arrive in phase. You can see there also what is happening. The peak from S2 has just arrived. Okay, this is the peak. But from S1, the mean position has just arrived. So they reach there also with some phase difference. And if there's a phase difference, O cannot be the central maximum anymore. Okay. With what phase difference do they arrive at O? Whatever is the phase difference between the sources, you will see the same phase difference at O. Okay, this we had discussed earlier. These such problems we had solved earlier. So suppose the sources have a phase difference of delta phi naught. Then at the point O, the waves now arrive with a phase difference of delta phi naught. Okay. Usually at the point O, they arrive with zero phase difference. If the sources are in phase, they arrive there with zero phase difference. At some other point on the screen, there will be a phase difference of delta phi naught. Now what happened? At O itself, you are getting the phase difference delta phi naught. That means at that some other point, the phase difference will now be zero. And in fact, This some other point where the phase difference is delta phi naught will be above O and also below O. Here also you'll have phase difference delta phi naught. Okay, there is a symmetry in the pattern you see above the perpendicular bisector and below the perpendicular bisector. So now what you're doing is, by making the sources out of phase, you are creating a phase difference at the point O. If phase difference at point O is now delta phi naught, then the zero phase different point will either be present here now or here. Which way it exactly goes depends on which source is ahead in phase. Okay, they won't ask you in that much detail, but they can ask you how much the pattern will shift if you introduce some phase difference, some amount, certain amount of phase difference. Okay, so the idea here is same as the idea we used to answer that glass slab question. Okay, so the thing you need to do is find out with what phase difference they arrive at O. If you know with what phase difference they arrive at O, then you can tell where the central maximum would have shifted to. How do you do that? First, find out with what phase difference they arrive at O. In this case, it's simple. Whatever is the phase difference between sources, same is the phase difference with which they arrive at O. Once you get that, okay, go back to the normal original pattern. Find out where you would have found that much phase difference in the original pattern. The central maximum will now go to that place, will now be found at that place. Pradyun is saying behind sources, the wave should travel extra distance. See, we have not discussed the experimental setup of YDSE yet. Okay. We are just considering two hypothetical sources which are not in phase. How these were created is what you're talking about. We'll come to that. What you said is correct only. The distance traveled before arriving at S1, S2 should have been different. That is when this happens. Correct. Okay. So the solution is very similar to what we did in that glass slab case. What did we do there? When the glass slab is introduced, we found out how much phase difference they arrive at O. How much phase difference is being introduced due to the glass slab. Then we found out where that much phase difference will normally be found. Pattern shifts to that place. Same thing happens here also. If the sources are uh, if the sources are having some phase difference between them. So this is a slight variation from the standard YDSE experiment. In the standard experiment, we assume sources are in phase. Here they are not in phase. Okay. They're still coherent, means the frequencies are equal, means the wavelengths are equal. Next case. What if the sources are non-coherent? Non-coherent means their frequencies are not same. Then what will you see on the screen? Like how will the pattern differ? Think carefully. What if the sources are non-coherent? If frequencies are not equal, non-coherent means not equal frequencies, the time periods will be different. So the time in which S1 creates a pulse is not the same as the time in which S2 creates a pulse. Fine. Let's consider two sources like this, S1 and S2. Let's assume the waves from these sources travel equal distances, okay, and reach some common point or common distance. Okay, let's say this is the wave emitted by the source S1. you can see there is a certain number of pulses. And let's say this is the wave emitted by the source S2. You can see there is a certain number of pulses. If they have the same frequency, they'll emit waves of the same wavelength. Then the number of pulses from S1 in that distance will be equal to the number of pulses from S2 in that distance. Okay. And what more can we say? If the sources are in phase, in this diagram, the sources are in phase. S1 has just produced a crest. S2 also has just produced a crest. The sources are in phase with each other. If sources are in phase, then after covering equal distances, they will arrive in phase with each other. Okay, you can see the mean position from S1 is arriving here and the mean position from S2 is arriving here at the same distance. Okay, so they'll arrive in phase. That's okay. Now, if the sources have a difference in frequency, that means there will be a difference in wavelength. Then the number of pulses from S1 in a certain distance won't be equal to the number of pulses from S2 in that distance. Okay, so we can visualize the situation like this. Let's say S1 has the same frequency. Assume S2's frequency is higher. If frequency is higher, the wavelength will be higher. So, okay, let's say S2's frequency is lower. If frequency is lower, the wavelength will be lower. Then when they travel the same distance, you can consider something like this. There's a clear difference in the wavelengths now. Okay. Okay, wait, they are inversely proportional. Good, correct, correct. Thanks for pointing out. If frequency increases, wavelength decreases. Okay. Speed is same, right? So let's say S2 has higher frequency, so shorter wavelength. Now you can see, even after traveling same distances from the sources, there's no guarantee they will arrive in phase with each other. Now, if you observe, the crest from S1 has arrived here. Okay, wait, we have taken crest and crest. Fine, let's see. At a random instant, a crest and crest have arrived from the sources at the same time. Let it be. Now imagine these waves traveling forward. Let us shift them forward. They have to be shifted with the same wavelength. As it is, they have to be shifted. Okay. Now see, I have shifted both of them by the same distance. But this time, at that common point, they are not arriving in phase. A crest from S1 is about to arrive there, but the crest from S2 has already arrived there. So they are now reaching there with a phase difference. Even though the distances are same, they are reaching there with a phase difference. Initially, means the first situation that we considered before the waves were moved. Okay. They arrived there in phase. As the waves travel and as they travel forward by equal distances, you see that they may not arrive there in phase. They will not arrive there in phase. Okay, at the next moment. After some more time, it is possible that they arrive in phase. Let me see if there are any such points. I'm just moving both of them forward at the same rate. Okay, yeah. So when they move forward by this much, you again see a crest and a crest arriving there at the same time. Right? So if waves from two sources of different frequencies arrive at a common point, sometime they will arrive in phase. Like at some instant they'll arrive in phase, then they'll go out of phase. Again, after some time they'll arrive in phase. So there is no consistent or there's no constant phase difference with which they interfere, with which they superpose. So if source frequencies are different, okay, the phase difference with which they reach a particular point is not constant. if the phase difference with which they superpose is not constant, the amplitude that you get at that point, the effective amplitude you get there won't be constant. The effective intensity you get there won't be constant. What is the formula for effective intensity when two waves superpose? I1 plus I2 plus 2 root I1 I2 cos of the phase difference with which they interfere. Superpose. Okay. Now, if the phase difference with which they superpose is constant, then you will see a constant effective intensity there. That is when you see a pattern like this. At some points, you see a constant high intensity. That is what you call as a maximum. At some points, you see a constant low intensity. That is what you call minima. So you'll be able to see that pattern on the screen. But if the frequencies of the sources are different, at one point itself, sometime they'll at the same point on the screen, once they'll interfere in phase, sometime later they'll be out of phase, sometime later they'll again be in phase. Okay, so there is no consistent phase difference, there's no constant phase difference with which they interfere. It'll keep changing, and if it keeps changing, the intensity also keeps changing. At the same point on the screen, the intensity keeps changing. Okay, I'm not talking about intensity varying from point to point on the screen. At one point itself, the intensity keeps changing, and it changes very frequently, because the frequencies that we are talking about are frequencies of visible light. Okay, it's in the order of megahertz, 10 power 6 hertz. Okay, so individual waves have that much frequency, and there's a difference in the frequency between the sources. Then the phase difference with which they arrive at a particular point will keep changing with a high frequency. The intensity at a particular point varies so frequently that your eye won't even be able to see that the intensity is varying. What will you see? You will see a constant intensity at a particular point, and you will see the same intensity everywhere on the screen. Okay, understand what I mean to say? Suppose the phase difference is a variable. The phase difference with which they arrive at a particular point is a variable. That is what happens now if the sources have different frequencies. If this is a variable, then the effective intensity you get will be a variable. You can average it. The average effective intensity becomes, see, effective intensity is a sum of three terms, I1, I2 and 2 root I1, I2 cos delta phi. If you want to average the sum of three terms, you have to average the three terms individually. I1 is the intensity emitted by the first source, that is fixed. I2 is the intensity emitted by the second source, that is fixed. 2 root I1, I2 also is fixed. You have to average cos delta phi. This is a variable. And the average of cos function in one cycle is 0. Whether it's a sine function or cos function, average is 0. Then this whole term becomes 0. That means the effective intensity you see on the screen will be I1 plus I2, irrespective of which place on the screen you are at. That means you will see the same intensity everywhere on the screen. You won't get an interference pattern. Okay? If the sources are not coherent, you won't be able to see a pattern of dark and bright bands at all. Because at any point you take on the screen, the waves won't arrive with a constant phase difference. They will arrive with a frequently varying phase difference. And that phase difference varies so frequently that you can't even perceive the changes in intensity that are happening there. You will see a constant intensity. And usually in a room, okay, if you switch on two bulbs, or even if you switch on one bulb, okay, you won't see a pattern on the wall, no? You will see uniform brightness on the wall. Fine. Of course, if you go very far away from the bulb, the brightness will decrease. That's a different case. Even close to the bulb, you won't see a pattern. Why? A bulb in real life has a filament. Okay. Every point on the filament emits light. So the first thing is there are infinite number of sources, infinite number of point sources on that filament. Even those infinite number of point sources, they are not in phase with each other. How can you guarantee that all the points on the filament of a bulb emit light in phase with each other? No, they become non-coherent sources. Okay. So the pattern that you see on the wall, okay, the pattern of light that falls on the wall, you don't see bright and dark bands, you will see uniform intensity. So if the two sources, even if you consider just 2 point sources, a bulb in real life is not a point source. Okay. Single bulb itself is a collection of infinite number of point sources. But if you somehow create 2 point sources also, if they are not in phase, sorry, if they are not coherent, you won't see an interference pattern on the screen at all. You will see uniform intensity, and that uniform intensity will be the sum of individual intensities of the sources. Remember this point. If they are coherent only, you will get a pattern. At some points, you will get a maximum always. At some points, you will get a minimum always. If the sources are incoherent or non-coherent, no pattern at all. Uniform brightness will be seen on the screen. Okay. Now let's talk about what Pradyun mentioned a little while earlier. To see a pattern, we need coherent sources. If they are in phase, even better. If they are not in phase also, pattern will form. Coherent is compulsory. Now, this is all a theoretical idea that we discussed till now. If you create sources of light, they should produce, if you create this kind of sources of light, they should create this kind of pattern. So Young also had this idea that a pattern like this should arise. And if this happens, we can conclude that light is a wave. Okay, the entire chapter is about proving wave nature of light or checking wave nature of light. So theoretically, this is the idea that he had. How to practically implement this? How to practically or actually get 2 point sources of light? Okay. Basically, what he did is he considered two very narrow slits. That's why it's called Young's double slit experiment. So you consider an opaque material here, and in that opaque material, let's say 2 holes are created or 2 narrow slits are created. Basically 2 small gaps, that's all. The narrower the slit, the better. The closer it becomes or the closer it gets to a point source. So you need 2 very narrow slits like this in an opaque material. Okay, the slits are numbered as named S1 and S2. Fine. So they can behave as point sources, or you can get close to that behavior by making the slits narrow and narrower. That is one idea. Next, we need them to be coherent. We need them to be point sources. We need them to be coherent also, means they should be emitting light of the same frequency. How do we do that? In real life, suppose you take a bulb which emits some color. Now each color has its own wavelength, so each color will have its own frequency. So you should ensure that there is a source which emits only one wavelength, right? So what Young did is he took one source of light. Now in real life, there are no point sources of light. You may use a bulb. Okay. Suppose there's a bulb which emits a single color, a single wavelength. That is possible. Okay. So place the bulb somewhere here. So this is the original source of light. Now the bulb could be emitting waves in will be emitting waves in different directions. Right? Then what Young did is he created one slit at some distance from the bulb. Okay. Why is this slit needed? Let's call this as, okay, let's call the original source as S, no, S naught, and this slit as S. Why do we need this? The waves traveling towards this slit from the bulb will approximately travel the same distance. Okay. Or actually, this distance has to be quite large compared to the bulb, size of the bulb. then what happens? The waves arriving at this slit will be a bunch of parallel waves. Actually, the source emits waves in all directions. Some waves will travel to this slit. So the waves reaching this slit will almost be parallel to each other. If they are parallel to each other, they'll have a planar wavefront. Then you can guarantee that the points in this slit produce waves in phase with each other. Okay, there's a wavefront arriving there. Wavefront means all the points will be in phase. Okay, so S behaves as a point source. Now the distance from S to S1 is same as the distance from S to S2. So S to S1 some waves will reach. Okay, light will travel this way. And from S to S2 also some light will travel. This is how we can ensure that S1, S2 are in phase with each other. Now, how do we do that? Here, all the points are in phase. And if these distances are equal, let's call these distances as D1 and D2. If D1, D2 are equal, then when they arrive at the slit S1 and at the slit S2 also, they will arrive in phase. That is how Young created two point sources which oscillate in phase with each other. And this pattern was actually found to be formed. Okay, and that is how they confirmed the wave nature of light. Okay. Now they may ask you questions based on small variations in this experimental setup also. Okay. What happens if this sheet, this opaque sheet with two slits that is there, what happens if it is brought down a little bit? What happens if this sheet is taken up or down a little bit? Such questions also can be asked. Let us discuss. So you observe what happens. Just a moment, let me copy all this. Now, in this kind of setup, you know that you will get the central maximum at this point O. Here. Now, why does that become the central maximum? Because all the way from the main source S0, the distance traveled by the waves reaching that point through S1 and through S2 is equal. Okay. What I'm saying is this distance is same as this distance. There is a symmetry. That is how that point becomes the central maximum. Okay. And to decide where the final central maximum will be, this distance is what, I mean, these distances are what you need to compare. That actually it's not even the distance, it's the number of pulses. The total number of pulses from S0 to O should be same in both the paths. That point is what you call the central maximum on the screen. Okay. Now we are not introducing any glass slab or anything, so wavelengths are same everywhere. If wavelengths are same everywhere, then same distance ensures same number of pulses. But if you put a glass slab somewhere, no, even if the actual distance is same, number of pulses won't be same because in the glass slab will introduce some extra pulses. That's a different case we'll discuss. Okay. Uh, just give me a minute. I'll drink some water. Okay. Now, think carefully and tell me what will happen to the pattern. What will happen means, does it shift upward or downward if this source is taken upward. What happens to the pattern you see on the screen? Try. What do you think will happen if this sheet that is there, this opaque sheet with two slits, what do you think will happen if we take this one upwards? How will the pattern get affected? Okay, I'll give you some ideas using which you can think. Now, S here is almost like a point source. Okay, actually, you have to consider only one source being here. It's a very narrow slit. Okay, S1, S2 are also point sources only. And I told you the central maximum will form, okay, or the central maximum is a point to which the number of pulses from S0 through S1 is same as the number of pulses from S0 through S2. And because there's no change in medium, okay, the distance to that point, the distance traveled by light to reach the point through the slit S1 should be equal to the distance traveled by light to reach the same point on the screen through S2. So if we raise this up a little bit, now what you see here is the original pattern. We want to find out what happens to this original pattern. So just a moment. So imagine this sheet being raised up a little. So you are creating an asymmetry in the situation. Fine. Now look at the distance traveled by light just to reach S1. It's this much. And look at the distance traveled by light just to reach S2. Clearly, to arrive at S1 itself, light has to travel a greater distance than to arrive at S2. Fine. The central maximum on the screen is a point to which the total distance traveled by light is equal. Okay, total number of pulses should be equal. So in this case, the total distance should be equal. Now, to reach S1 itself, light has traveled extra distance. Then after passing through S1, it should travel lesser amount of distance compared to the light coming from S2. And that is only possible if you take a point on the upper side of the screen. So you take a point somewhere here. Okay, randomly I'm drawing. S1 to that point is less compared to S2 to that point. Okay. So basically we have to compensate. From S to S1, the distance was more compared to S2. Therefore, on the other side, the distance has to be less on the upper side, more from the lower side. So this is where the central maximum will form now. So basically, if you lift this sheet up, the entire pattern will shift upwards. Okay, you have to imagine light traveling from the original source to the screen through the first slit and then through the two slits S1 and S2. Then you will be able to tell what happens to the pattern. Is this clear? Rishi, did you understand?
Yes, sir.
Okay. Next, okay. Think on the same lines and try to comment on what will happen to the pattern if we shift this sheet up. Let me draw the diagram corresponding to that. Okay, we don't have to. Fine, let the original pattern be there. Now this sheet is at its original place, symmetrically arranged. The first sheet is raised up. As a result, what will happen to the pattern? Any ideas? Answers. Idea is the same. You have to think about the total distance traveled by the waves, traveled by light. Okay. Imagine light traveling from the original source. Now, the light going through S2 or through S1, it has to travel through S. So this distance is same. Fine. After that, since we moved the sheet upward, the distance traveled here will be less compared to the distance traveled to S2. Then we have to compensate for it on the other side. So on the other side of S1, S2, the distance from S2 should be lesser, distance from S1 should be greater. That means the central maximum will be seen somewhere on the lower side of the screen. Like this. So if you raise that sheet up, the pattern will shift down. Okay, so you just have to imagine light traveling, that's all. Based on that, you can answer any question. Okay, so this is all you need to know about Young's double slit experiment, how the pattern forms, how it was actually executed, what happens to the pattern if you make some small changes in experimental setup, fringes, fringe width, the relation between y coordinate and delta x, y coordinate and phase difference, and not just y coordinate is the linear position on the screen, theta also, angular position relation also you need to know. Okay. So do all the derivation, revise this once. Next class, we will discuss single slit diffraction pattern. Okay. Thank you all. We'll continue in the next class.
Thank you.